energy per bit is basically the amount of energy, the average amount of energy expended by the transmitter to send one bit. So what does that mean? It is, well, think of the hardware model. So at the transmitter, we have modulation to digital to analog to physical layer access. So the issue that we're dealing with is that, oh, excuse me, on this side everything's discrete, and on this side everything's continuous in terms of time. So on this side we're dealing with discrete time. Here's the computer software domain over here. On this side this is the physics domain. Signals only have a well-defined energy over here. It's energy as far as the electrical currents and voltages are concerned. It's a key problem because if you're not careful, you can make funny arguments about funny arguments that don't hold up physically. So if you're not paying attention to the energy, you might not compare two systems fairly. In other words, you can say that you can propose two modulation functions and claim that modulation function 1 does better than modulation function 2, but miss the fact that the first modulation function actually uses far more energy. And if you bumped up the energy of the other one by amplitude scaling, it would actually do better. So energy per bit provides you with a fair comparison to ensure that you're comparing two systems based on the same amount of energy that they're using. So the problem is, throughout this course, I want to deal over here. I want to deal with the discrete domain. I don't want to go too far into the continuous domain, but energy is a concept that only really exists over here. So how do we bridge that? Well, first of all, let's talk about what energy means. So for a continuous signal, continuous time signal S of t, the energy in S of t is equal to the integral over all time of S of t squared. Y squared? It basically has to do with the fact that at constant voltage, electrically speaking, at constant voltage, power is equal to current squared times resistance. So if voltage and current and resistance are constant, which is what usually happens, the current will vary, and then the power will be equal to the current squared. And then the total energy, power is energy per unit time. In order to get energy, you integrate power over time. So in some sense, signals that we're talking about here can be thought of as electrical currents in continuous time. Okay, that means, actually I should have erased that. So here's modulation, here's D to A, and here's physical layer access. So going into modulation, we have the bits B. Coming out of modulation, we have S0 of K and S1 of K. In other words, discrete time signals. By coming out of digital to analog, they're transformed into continuous time signals. So over here, they're defined from over K equals 1, 2, up to NB. And over here, they're defined from T equals 0 to TB, the bit time. what's the energy in S0? Let's call E0 equals the energy in the continuous time waveform that you use to transmit 0. That's the energy in S0t. And from here, that's equal to the integral from minus infinity to infinity strictly, but it's only non-zero from 0 to TV of S0t squared. And similarly, let's call the energy in bit 1 to be the energy in the continuous time waveform S1 of t, which is the integral from 0 to TB of S1 of t squared dt. So, if I want the average energy per bit, I'm going to call that E sub B. How do I get that? EB. How do you think I would get that from E0 to E1? Yeah, so it's the average over those two. But is it an equally weighted average, or how do I weight the average?
Probability of 0 times the energy of 0, probability of 1 times energy of 1.
Exactly. So it's probability of 0 times E0 plus the probability of 1 times E1. So for instance, if you had lots and lots of energy in E0, but it occurred very seldom, then E0 would be large, but P0 would be very small, so that wouldn't actually contribute very much to EB, the average energy. Okay, so now the problem is, I know how to calculate energy from, so this is the physics side, the electricity and physics side. So the question is, how do I get from S0, okay, let's say, to S0t? So, does anybody know how, do you guys know how analog to digital converters work? Yeah? Okay. There are actually a few ways that they work. But what we're going to do is we're going to avoid any lengthy discussion of how they work exactly, and we're going to assume the following. So we assume